Let's now take a look at some of our friendliest functions to take the antiderivative of, just like they were the friendliest functions to take the derivative of. And we're going to look at some power functions here, where we have x to some power. So for example 1, we're asked to compute the integral of x squared dx. So we want to find antiderivatives, and we just found in the last video that we have one antiderivative of the form x cubed over 3. And we know that all of the rest of the antiderivatives will have the form x cubed over 3 plus some constant. So we put a plus c here on the end, and now we have accounted for all of the antiderivatives. Great. Well, that was fun. Let's think maybe a little bit about how we got here. What did we do in order to do this? We know that the power rule for derivatives says the derivative of x to the n is nx to the n minus 1. So it says you reduce the exponent by 1 and you multiply by the old exponent. So when we are reversing this process, what we did here was instead of decreasing the exponent by 1, we increased it by 1. Then in order to account for this constant out front that you get when taking the derivative, we divided by that new exponent. So let's put that sort of general principle into practice here and think, well, if I wanted to take the integral of x cubed, then maybe what I would have is I need to increase the exponent by 1, because when I'm taking the derivative of x to the 4th, I get something involving an x cubed out. And to account for the constant, we need to divide by 4 here, because if I'm taking the derivative of x to the 4 over 4, I get 4x cubed over 4, which is x cubed. Since I wanted to find a function whose derivative was x cubed, this x to the 4 over 4 is exactly what I'm looking for. Likewise, for if we want to do the integral of x to the 37, well, great. We can continue to use our pattern and increase the exponent by 1. So x to the 38 divided by our new exponent, 38, plus a constant c. Example 4 doesn't look quite like the others. It's looking like, we don't have any x's here to any powers, but maybe secretly we do. Actually, before we talk about where the x's are hidden, let's actually do this. We want to find a function whose derivative is 7, and we know one of those. We know that if I took the derivative of 7x, I would get 7. So my integral of 7 here is 7x plus c. But another way to think about this problem would be to think about this as the integral of 7x to the 0 dx. X to the 0 is just 1. And so if we were to use this pattern that we have, where we're increasing the exponent by 1, we would be left with 7x to the 1, divide by the new exponent, 1, and add c. And this is exactly the same as what we had above, 7x plus c. So here, the power rule for integrals is secretly getting used. We just don't quite see it because that x to the 0 is kind of invisible. Last, example 5, compute the integral of x to the minus 1 dx. Great, so we have a pattern going here. Let's continue to use it. Let's increase the exponent by 1. So we're going to increase it by 1 and divide by the new exponent and add c. And there should be a little bit of a red flag here because we've divided by 0. And the one thing we know we can't do is divide by 0, so we had better think about this in a little bit more depth here. So there seems to be a problem with minus 1. In particular, it's the problem that when you try to apply this pattern that we've applied, you end up with a 0 in the denominator. So let's think a little bit more about this, and we have the integral here of x to the minus 1 is the same thing as saying 1 over x. So I'm looking for a function whose derivative is 1 over x. And, in fact, I know one of those. It's natural log of x. So we might think that the integral here is natural log of x plus c, but there is a subtlety going on here that if you had a good Calc 1 teacher, then you have already encountered. And if you didn't, like for instance me, there's a subtlety here that we're going to need to talk about briefly. Namely, there's a problem of domain. The function 1 over x, if I were to draw a graph of it, looks something like this. So 1 over x. And the function natural log of x, it looks something like this. But the function 1 over x has negative values in its domain, where the function natural log of x does not. So when we're finding an antiderivative of 1 over x, we need it to be some function whose domain is everything except for 0. And natural log of x isn't going to cut it. Natural log of x doesn't have any negative x values in its domain. So what we need to do is we need to think about, well, what exactly is happening for the function 1 over x when x is negative? And the way that we're going to do this is we're going to say, well, let's think about this function here. Let's call it f of x being natural log of negative x. So natural log of negative x, this is defined for x values less than 0, because if I plug in some negative x value, I take its negative to get a positive out inside the natural log, and then I can take a natural log of a positive number as normal. So what happens here if I take f prime of x? Well, to take the derivative, I notice that I have an inside function and an outside function. Namely, my inside function here is negative x, and my outside function is natural log. So if I'm taking the derivative, my chain rule says take the derivative of the outside and multiply by the derivative of the inside. So the derivative of natural log of stuff is 1 over that stuff, and I need to multiply by the derivative of the inside, and the derivative of minus x is minus 1. So putting this all together, I notice that I have a negative 1 in my numerator, a negative 1 in my denominator, which cancels out, and I'm left with 1 over x. So the derivative of this function natural log of minus x here is also 1 over x. Furthermore, natural log of minus x satisfies the requirement that we need, which is that it's defined on negative numbers. If we were to draw a graph of it, natural log of minus x would look something like this. Cool. So we have an integral of 1 over x for x values larger than 0. We have an integral of 1 over x for x values that are less than 0. So now we need to put these two functions together into a single function. And the way that we do that is we draw the function y equals natural log of the absolute value of x. Natural log, the absolute value of x, it makes every x value positive, which means that for positive x values, it leaves them alone, and for negative x values, it takes the negative of them. So here, my graph of natural log of the absolute value of x is exactly natural log of x for positive x values, and it's natural log of minus x for negative x values. And now that I'm looking at it, I realize I drew my graph of natural log of minus x incorrect earlier. It should pass through the x-axis here. So in any case, natural log of the absolute value of x is exactly the function that we're looking for. It has its derivative for positive x values is 1 over x, and its derivative for negative x values is also 1 over x. So when we're doing this integral of x to the minus 1, the answer that we're actually looking for is not natural log of x, but natural log of the absolute value of x. All right, so that was a lot, but we have a general pattern here, namely that whenever x, or whenever our power on x wasn't minus 1, we were able to use this pattern, increase the exponent by 1, divide by the new exponent. However, when the exponent was negative 1, we had this weird kind of special case. So let's go ahead and state that as the power rule for integrals. We're going to say if n is some real number, and n is not minus 1, then the integral of x to the n dx is going to be equal to, we increase the exponent by 1, we divide by the new exponent, and then we add c. to account for the fact that we have many different antiderivatives. All right, so that's all for this video. We'll come back in the next one and talk about the integrals of some other common types of functions that we're going to be running into in this course.